Alright, so in this lesson we're going to start dealing with forces between parallel conductors or parallel wires with currents. And so let's say we go back to our situation where we have two wires. The wire on the left has a current that's going into the page, and the wire on the right has a current going out of the page. And I want to look at what is the force on one of these wires caused by the magnetic field created by the other wires. So remember that moving charged particles create a magnetic field, but magnetic fields put forces on moving charged particles. So if we look at the magnetic field caused by the right wire, at the location of the left wire, it's acting downward at this location. And so we can actually show that by the right-hand rule. Well, if the magnetic field's acting downward and we apply the right-hand rule to that situation, what we find is that there's a force on the left-hand wire that's acting outward to the left. If we did the same thing for the right-hand wire, the force or the magnetic field caused by the left-hand wire at the location of the right-hand wire is downward. If we flip things around, it is downward. And so if we flip around our direction that our current goes and use our second right-hand rule, we find that the force that the right-hand wire experiences from the left-hand wire is also outward to the right. Now, if we actually wanted to calculate how big this magnetic field is, well, it's not that hard to do. Let's say they both have a current of I. Well, I have IR for the right-hand current and IL for the left-hand current. And so we have mu naught I times 2 pi R is the magnetic field. So the magnetic field caused by the right-hand wire is mu naught IR divided by 2 pi R. The force would be I times L times B. Unfortunately, we don't know the length of the wire. If these are infinitely long wires, this would suggest they experience infinite amount of force. But what we can do is calculate what is the force per unit length that the wire experiences, which would just be current in wire L divided by times the magnetic field caused by B. So I multiply by IL, I get mu naught IR IL divided by 2 pi. Now it's worth pointing out that the same force exists on the right-hand wire caused by the magnetic field of the left-hand wire. If you work it out, you get the same exact value, just opposite direction. And that's actually kind of cool because it's consistent with Newton's third law. If the right-hand wire is putting a force in the left-hand wire must be putting an equal and opposite force in the right-hand wire. Now, if we flip this around and made it two parallel conductors, both with current going in the same direction, what you'd find is you get an attractive force between those wires. So, next we're going to look at the magnetic field caused by a circular loop. I kind of said in the last lesson we would maybe look at this, and we are going to look at it here. There is a full derivation that's found in your textbook, or you can look it up online. I am not 100% sure on this citation because we don't have a paper copy of the book, and the version of the book is different than the version I have online. So I'm not 100% sure about that citation for the full derivation, but we can go through it in class if you'd like to. Now, if you're on the x-axis and the x-axis goes through the center of the loop, what you find is you get that equation for the magnetic field, and what you find is the magnetic field, if current is going around this loop in that direction, you find that magnetic field is actually pointing in the x direction at this location. Now, what if we want to look at the very center of the loop? And so what does it mean to be in the center of the loop? Well, it means x is getting close to 0 or equal to 0. If you plug in 0 for x or do the limit, what you get is that the magnetic field at the center of the loop is mu naught I divided by 2a, where a is the radius of your loop. So really the only things that matter are the current in the loop and the radius of the loop. The bigger the loop, the smaller the magnetic field. The larger the current, the larger the magnetic field. And so that gives us one way to calculate, or gives us one way to find the center of the loop. Now, if you had many loops together, let's say instead of just being one wire in this loop, let's say it was 50 wires that made up this loop, and all 50 carry that current. Well, the way you would deal with that is you just take and multiply this number by 50. because really in that loop, the amount of current is 50 times bigger than the current in any individual strand of the loop. So if you took and made a loop where you wrap the wire around 50 times, you'd get 50 times the magnetic field. So more loops of current generally relate to more magnetic field. We'll look at here in a little bit what we call a solenoid, which is where you take a bunch of loops and you start to spread them out a little bit, so they're not all at the same location. Now, as you might have guessed, calculating using Biot-Savart law is kind of a pain because you have to do an integral. While we haven't done any of the nasty integrals in this lesson, you can kind of envision what you would go through if you think back to calculating electric field using integration. Now, if we remember with electric field, there was an easy way to get around it called Gauss's law that simplified that calculation. Happens to work out with magnetic fields. The same thing is true. I think that I actually need to change this equation. I would actually call it a line integral and not a surface integral. We'll talk about the distinction here between the two. Well, no, I don't, because I have dl instead of dA. Never mind. So similar to Gauss's law for electric field, we have a simplified version called Ampere's law for magnetic fields. For lots of situations, this is easier to use than the Biot-Savart law. The Biot-Savart law I usually call the sledgehammer for calculating the magnetic field caused by a current. This is the fine hammer for calculating the magnetic field from a current. And even though it looks pretty complicated, it's actually simpler than what it looks. As kind of Gauss's law, even though Gauss's law looked more complicated than doing the integration, Gauss's law usually was simpler than what it looked. And we'll look at that in the next lesson and look at how we can apply Ampere's law to solve various types of questions.